So now we are going to talk about the next group. We talked about lipids. Now we're talking about carbohydrates. Okay, so I changed my pointer. Hopefully you can see it a little bit better. So what are carbohydrates? Well, carbohydrates are made from simple sugars. Okay, simple sugars have this type of formula if you want to try to figure out how many hydrogens and oxygens are in a sugar. So if it's got 5 carbons, it's going to have 10 hydrogens and 5 oxygens. You're not going to have to be able to figure that out, but there is kind of a generic formula for these sugars. Okay, so we're going to start on the most basic level. Again, the small units that make up big biomolecules or big biopolymers, which is usually what we refer to as a carbohydrate. And so we're starting with monosaccharides, meaning one sugar. Saccharide is sugar. Mono is, of course, one. So these are the smallest units. You cannot break them down anymore. So the smallest unit of a carbohydrate can't be broken apart, or another word for that is hydrolyzed, because you have to have a water in order to actually break them apart. That's why it's called hydrolysis. But you cannot break these simple sugars apart, the smallest unit of sugar. And so how do I describe these sugars? They all have between 3 and 8 carbons. Okay, they've got 3 carbons. They are called a triose. 4, they're called a tetrose, and 5, they're called a pentose. Now, this ose suffix might sound familiar to you, especially because in organic, ose means that we've usually got a double-bonded O somewhere in there. Okay, so aldehydes and ketones are what we are going to be looking at. We definitely have some aldehydes and ketones in these sugar molecules. They all have at least 2 OHs or alcohol groups. And then, like I was saying, those ose means they're like aldehydes or ketones. And in sugar form, they are called either aldose or ketoses. So aldose if their double bonded O is on the end, and ketose if it's somewhere in the middle. So if I look at these molecules here, these are some examples of sugar monosaccharides. Okay, this one has 1, 2, 3, 4 carbons. So this would be considered a tetrose sugar. Okay, my C double bonded O is a ketone because it's between 2 carbons. So that would be called a ketose. And that's really all I would say about this one. This one over here is considered an aldose because the carbon with the double bonded O is on the end. Notice it just has a hydrogen over here. And this has 1, 2, 3 carbons. So this is called a triose. Okay, so it's either an aldose or a ketose, and you can tell me how many carbons are in it. Now, they can be connected differently. So we're going to have some chiral carbons here. And if you don't remember what the term chiral means, it really is based on the fact that it has 4 different groups. So if you have a carbon that has 4 different groups attached to it, it's a chiral carbon. Because in 3 dimensions, they're non-superimposable is the reasoning behind that. But as long as you know 4 different groups on a carbon, it's chiral, you're good. So since that is the case, and we have chiral carbons, we need to be able to differentiate between ones that are chiral in one way and ones that are chiral in the other way. So this is how we tell the difference. So our 2 isomers, or optical isomers, right, because of chirality, are either L or D. So what you look for is if the lowest chiral carbon has the OH, or that alcohol group, on the left, it is an L isomer. So let's look at these guys. Okay, the lowest chiral carbon. So I'm going to start at the bottom. This carbon here is not chiral because it has a bond to this group. It has 2 hydrogens bonded to it. So 2 of the groups are the same. So it is not considered chiral. It also has an OH. This carbon here, though, is chiral because it has this group up here, a hydrogen over here, this group down here, and an alcohol over here. All 4 are different. So this carbon right here is chiral. So I'm talking about this one. Okay, the OH is on the right. So that is not L, that would be D. My lowest chiral carbon has the OH on the right. This one would also be considered a D isomer because this is my lowest chiral carbon. The OH is on the right. Okay, so there's kind of 3 descriptors we can use for each of these sugars. That's how many carbons they have. So tetrose, triose, pentose, all of that. And if it's an aldose or a ketose, and if it is an L or a D isomer. So I could ask you to describe sugars in that way. So I would try examples 1 and 2 right now if you want to pause. So first of all, I'm asking how many carbons are chiral, and this is a glucose molecule, C6H12O6, right? So I have 1, 2, 3, 4, 5, 6 carbons total. So this is a hexose. I didn't ask that, but this is a hexose. There are 4 chiral carbons, meaning 4 different groups. So each of these carbons here has 4 different groups on it. This one here is not chiral because it's got 2 hydrogens, and this one is not chiral because it has a double bonded oxygen and it only has 3 groups on it total. Okay, so it has 4 chiral carbons. I look at the lowest chiral carbon, my hydroxide is on the right, so it is a D isomer. Okay, over here, this is ribulose. I have 1, 2, 3, 4, 5 carbons, so it's a pentose. And I've got my OH on the lowest chiral carbon is on the left, so that is going to be an L isomer. Okay, now looking at the structure, you might be like, well, glucose doesn't look like that. And usually glucose actually doesn't look like this. You're right. In solution, so anytime they're in water or something like that, these sugars and other monosaccharides become cyclic. So this hydroxide is going to bond to that carbon, and you actually get a structure that looks like this. So a lot of the times we draw them like this, but they become cyclic structures. And these are the things we see in the body. Okay, so this is just to differentiate between sugars, and this is what we see in real life. Okay, so we started with monosaccharides. Now we're going to go into bonding those together, making disaccharides and beyond. So a disaccharide would be when you have 2 monosaccharide units joined together, okay, 2 sugars. Now that means that it is something that could be broken down. It can be hydrolyzed. It can be broken into the 2 separate monosaccharides. Okay. Very common disaccharides that we see all the time are sugar. That is a combination or a bonding of a glucose molecule and a fructose molecule. Lactose is milk sugar. A lot of people are allergic to it. Is a glucose bonded to a galactose molecule. Maltose is glucose and glucose. There's all kinds of these disaccharides that we consume every day. Okay, so what makes them disaccharides? How do we make that bond? So I'm using over here, this is sugar or sucrose as an example. I have a glucose molecule and I have a fructose molecule. And I have highlighted here this hydrogen and this OH here. So what happens is these create a bond right here between the oxygen. Now I have an ether, right? Oxygen with 2 carbon groups on it. This is called a glycosidic linkage, and I produced a water. I took off this hydrogen and this OH and just bonded through the oxygen. This is called a glycosidic linkage. Okay, so if you think glucose glycosidic linkage, maybe that's a way to remember it. But that is how sugars bond together. Okay, you take an H2O out. Now, this kind of brings me to why it's called hydrolyzed when you take them apart, because to go in the reverse, to actually break these into their 2 molecules, you have to add a water molecule and break these. That's called hydrolyzing because you're adding a water. So when you have water and some type of acid catalyst, that's how you get them to split. So disaccharides can be hydrolyzed when you add water and some type of acid catalyst. Okay, so let's go bigger. We had disaccharides, now polysaccharides, meaning, of course, many sugars. So this is when you have a lot of monosaccharide units together. We call that a polymer, right? When you have a lot of building blocks bonded together, it's usually a polymer of glucose. Okay, and this is considered a complex carbohydrate. So that might be a term that you're very familiar with. Complex carbs are really just big polysaccharides. It's a bunch of glucose molecules stuck together, and that's how you get a lot of energy. Okay, there are 3 types of polysaccharides that we are going to talk about. That's plant starches, animal starches, and cellulose. Okay, so plant starches, now the term starch should kind of be synonymous with carbohydrates. Plant starches, the 2 most important ones that plants create are amylose and amylopectin. Amylose is just a long continuous chain of glucose units, like 250 to 4,000 units, just a huge molecule of glucose units. Now, amylopectin is a bunch of glucose units that kind of have branches. Okay, so it's going to be, they're more compacted in shape, you could say. You're going to have a bunch of different branches off there, like this one down here. This is a bunch of glucoses bond together, and then I got a branch off here. So they are like a specific type of starch. Okay, these are bonded through what are called alpha linkages, alpha 1,4 linkages, alpha 1,6 linkages. That's just the type of bond between which carbons on the molecule. So it's bonded between carbon 1 and carbon 4, carbon 1, carbon 4, you get an alpha linkage, or a 1 and 6 bond here, this is carbon 6, is also an alpha linkage. Okay, so those are the type of linkages in plant starches. Okay. Animal starches, like glycogen, okay, this is a really important starch in our bodies, are highly branched, and they're the most abundant polymer on Earth. Okay, glycogen is a bunch of sugar molecules bonded together. When you think of the term glycolysis, it's the breaking down of those sugar molecules. And finally, cellulose. Cellulose has a completely different bonding type to it. It has beta linkages. This is why we don't really like digest cellulose. We can't break it down because beta linkages are resistant to hydrolysis. A beta linkage links a different way. You don't have to be able to draw these, just know that they're different. I've got these sugar molecules or these glucose molecules, and they're actually bonded between these carbons and these carbons in a different orientation. So since it's a different linkage, we actually can't break down cellulose. It's fiber and it passes through without us being able to break it down.